just a reminder or a first time thing for people who weren't here yesterday. Was there anybody else that wasn't here besides Bo? And me. All right. Okay, so tomorrow and Thursday, you're going to be taking your test for topic 7. And it's going to be 2 parts. So you'll have 10 questions tomorrow and 10 questions on Thursday. I have already made the tests, so I can tell you exactly how they're going to be formed and what questions will be on them. If you just want to listen and possibly remember or possibly forget, that's totally fine. If you want to write it down, you might want to do that. So day 1, the first 6 questions are going to be numbers 1 through 6 from the practice. No. Sorry. The last 4 questions are going to be, please, with the noises, guys, are you serious? I'll wait until everybody gets their stuff so that it can be silent when I'm talking. I'm waiting. No, you finish what you're doing so I can. Okay. Good. So the first 6 questions on day 1 will be numbers 1 through 6 on the practice test. The last 4 questions will be from the quiz, and those questions will be numbers 1 through 4 of the quiz. Those will be the rest of the test questions. So I took questions 1 through 4 from the quiz and put them as the last 4 questions of the test tomorrow. Those questions were the ones that was like, if the parent function, or if there's a function f of x equals x squared, the parent function, and then g union comes along, and he's 3x squared, how is g union different from the parent function? Okay, it's like upward, downward, narrower, wider. Remember that you don't want to say upward if it's positive because that's not different from the parent. Even though it does open upward, it's not different, so we don't put that. You only put it if it's downward, if it's negative. And then for narrower and wider, you always put whether it's narrower and wider because that's always different from the parent function if the leading coefficient is something other than +1. And then day 2, the first 4 questions on day 2 will be from the practice test 7, 8, 9, and 10. That's what we're going to be going over today. And then the last 6 questions of day 2 will be, here's a function in standard form, what's the y-intercept? Which are the questions from the quiz 14 through 19. Remember how I bulked up the quiz with 2 of the easiest questions I could find and then just put as many of them as I could find on there? I took all of those and put them on your test. So that you would have some of them on day 1 and some of them on day 2, so that when you take day 1 and day 2, we're gonna average them together to get your score for topic 7 test, okay? So if you wanna use your quiz notes on the test, absolutely do it. I just gave you that structure so that you know what to look for when you see those questions, if you want to use notes from the quiz. Okay. So now that we've got attendance and everything, we're gonna go to questions 7 through 10 on the practice test. Is there anybody who needs a practice test?
Me. I'm short. Wait, what's that? I'll shake a fish in the head.
Do you think you guys could stop talking? Thank you. Elena and Lily, do you think you guys could stop talking also? Okay. Okay, so looking at the practice test, we already did questions 1 through 6, so here is where we left off. Number 7, I'm gonna do 4 problems, 7, 8, 9, and 10. It's gonna take the whole class period, but I will get it all done. So it won't be one of those things where you have to watch the video in order to see me work out one of the problems. I will still have the videos up if you want to hear me go over those explanations again. But the biggest thing you wanna make sure is that you are filling in notes from my Canvas notes. You can write as much down as you want during this class, but you're going to want to go back to my notes where I really detail all of those steps and the process of everything, the thought process and the actual execution process, okay? So just for these 4 questions, I have 1, 2, 3, 4, 5, 6 pages, just for 4 questions. Do you need to have 6 pages just for 4 questions? Mm-hmm. No. Can you? Yeah. Sure. Do you see how it's up to you? And you're gonna use your best judgment? Yeah. Tomorrow when you are taking the test, I will be asking to see your notes and you will show me what you have. I will use my best judgment to judge if you did a sufficient job copying down the notes that you will need for the test. If I just see a couple of quick things jotted down, I'm not going to be very happy about that, okay? Or I shouldn't say I'm not going to be happy, I'm just going to say your grade is going to reflect what you have down. So make sure you've got a good amount. That was terrible. I did it for one. Backboard. Boom. Off the backboard. Great. All right. So at the top of your paper, you can say something like
Test 1.
Topic 7, test, day 2. And now let's take a look at what number 7 looks like. The graph of h of x equals x plus 4 squared minus 7 is a transformation of the graph of f of x equals x squared. Let's define a few things that we have here so far. What does the word transformation mean? And you can just define it in any way. A change, that's exactly what it means. Are you guys done with all of the extra noise stuff there? Good, it's just very distracting. So a transformation simply means a change. So this is a change of this. What's this?
Parent function.
The parent function. So f of x equals x squared is the parent function. It's the mommy and daddy. And then h of x equals x plus 4 squared minus 7 is the little baby?
What's his name? Mr. Miller's
He's a little baby, that's his name.
Chicken.
Something with an H.
Hector.
Hector. Definitely
Hell.
Hector. Okay?
Hector.
This is happy little Hector. Okay?
What's
Congratulations, Mommy and Daddy. It's a boy. Okay?
Dr.
This is a
Misleading.
little baby named Hector. He's a little bit different than Mommy and Daddy. He's in a totally different spot on the coordinate plane. And it even tells us that it's a transformation. Now, sometimes a transformation isn't necessarily just a change of location, but in this answer, it actually kind of gives that information right here. The graph of H, the graph of the little baby Hector, is a translation, blank units left and blank units down. So, what does translation mean? Yes.
To move from one place to another.
Yes, a translation is a move or a shift. Very good. Is a move or a shift. Is a move or a shift. Okay. So if it's a translation, first, now, when you actually work out this problem on your tests, you don't have to draw the parent function, but it will make a really good visual so that you can see what's going on. The parent function, I'm not even gonna draw the whole parabola, I'm just gonna put the vertex of the parent function. Where is the vertex of the parent function? Always.
0,
0,
0.
0. So it's the parent function vertex is 0, 0. What does baby Hector tell us? Or what about baby Hector's function tells us where his vertex is going to be? Yes, babe? Mm-hmm. It'd be what? Yes, that's right. She's saying, well, this is in vertex form, and if that's vertex form, we know the vertex is H and K. If this is H and this is K, H stands for,
Heck.
get that sign the heck out of there. Yes, it's
You're welcome.
Get Hector out of there.
it's Hector for heck. Okay.
Hector on
Or heck for Hector, I don't know. So this 4 has a positive, and we need to get that sign heck out of there. So the vertex is going to be -4, and our -7 here, the K tells us to keep that sign. So the vertex is -4, -7. So I'm going to show that. -1, 2, 3, 4, -7. -1, 2, 3, 4, 5, 6, 7. Wow, all the way down here. Uh-huh.
Oh, me.
It does look like you.
Well, you gotta add.
You gotta add more curls, yeah.
Yeah.
More girls.
Not like that one.
That.
No, it just looks like a ceiling fan.
A bar
Okay. Okay. I really wish it said B of X, so it could be Baby Bobo. Okay. All right, so this is where the vertex of baby Hector is. I really don't care if it's pointing upward, downward, wide, narrow. I just really don't care. This is all about the transformation. It's all about the translation. In the answer, it says, the graph of H is a translation blank units to the left and blank units down of F. Well, F, the parent function is here. Let's see how many units it goes to the left. 1, 2, 3, 4.
Negative 4.
What?
I said I was just talking out loud. but-
No, I'm actually really glad you said that,
Is that
because
possible?
she's saying, what about the negative 4? Let me ask you a question. If I put negative 4 in here, would that be correct?
No.
No. What part of this already accounts for the fact that?
Left.
Yes, very good. So because it says that it's to the left, we're actually already pointing out that the 4 is the value of the h of the vertex is negative, but it's kind of, because it made it into like a whole sentence, it's accounting for that negative by saying to the left, so we actually don't write the negative. Because if we say negative 4 to the left, it's gonna go the opposite way,
So no
right?
positive, right?
Yeah, that would be really weird, yes.
So if I actually put that on the test, like for EOC, would they still count it?
If you put negative 4,
Yeah.
it would mark as wrong, and so would this.
Dang.
Yeah, so that's why we're going over it with the review. You have to make sure that whatever your vertex is going, if it's going to the left, then the negative is already accounted for. Now, what about the 7 here? I've got a negative 7, so after it went to the left 4, it goes down how many?
7.
Yeah, does it go down 7 or does it go down negative 7?
Goes down some.
Yeah, it goes down 7. The down accounts for the negative. So it's just 7 units down. Yeah. Just be careful with that camera. Okay. Does everybody totally understand that one?
Yes.
Again, these notes that I'm writing are just gonna be no good for you tomorrow. You need, because it's not enough, you need to fill in the explanations, okay? All right, we've got 1 down, 3 to go, we can do this. Number 8 is gonna be, I actually really enjoy, hearing everybody try to figure this out. It's fun for me. What is an equation for the quadratic function represented by the table shown? Now, if you're like me, you go, because it's giving you a bunch of numbers, got some x coordinates, got some y coordinates, or our input coordinates, our output coordinates. So we know these are coordinate pairs. If I wanted to, I could graph them. But how would I get my my numbers here? First of all, what kind of form is this in? Yeah?
Shoot.
What is the form of this function notation? Yes? It's vertex form. Just by the way, I'm gonna write some notes right here next to the table, but if you, just so you know, you cannot use this piece of paper as notes on your test. So don't copy any notes on this because you won't be able to use them. So this is vertex form. So it's gonna be a times x minus h squared plus k. So we're missing the a, the h, and the k. 3 things to fill in. Well, if it's vertex form, I know that 2 of those missing numbers can be filled in if I find the vertex. How do you identify the vertex? By looking at this table. Yes,
The
Jen?
turning point, so where it goes back up.
Yeah, where do you see the turning point?
0, 4.
I'm actually really glad you said that. It's not correct, but I'm so glad you said that. Every other class said it, and we worked through why that's not correct. And I think that what you guys have accidentally gotten stuck in your brain, because when we did day 1 of this lesson, it was all about the parent function, the parent function, the parent function. And we saw that the parent function was, the vertex was at the origin, the axis of symmetry was the y-axis, so we really always think of functions, for some reason, being on the y-axis, the vertex, and it's not, always. Yes, Angelina? What? okay, you wanna tell me what it is and explain how.
So the vertex is -170.
That is correct, how do you know?
Because the output repeats forward.
Yeah,
So that,
and so you can see starts with an S, parabola,
Symmetry.
the symmetry, very good. Because we see that we have matching outputs here, and we know that a parabola, you can go, Lily. We know that a parabola has to have symmetry. That means if they have the same output, somewhere in between those same outputs must be the vertex, because the vertex is always on the axis of symmetry line. Yes?
Wouldn't it be like -1 right after the X, and then the Y
Negative-
would be 7?
Yes, I'm getting there. Try not to go ahead just because when we do that, the people who are still trying to process what I'm saying get confused when we jump ahead too much, okay? So, if the vertex is -1, +7, that means what Carmine just said. We can fill in. Go ahead and say it now that we're ready to process it.
The last two boxes.
Yep, the last two boxes are
for your
H
X is 7.
and our K. Yep. So we have -1 and +7. Now, you might notice that if it's X minus -1, shouldn't that be X plus 1?
You have to change the sign because earlier before you turn it into a vertex, you say, get the heck out of here, that's the sign. So-
Yeah, well, we're kind of doing the opposite of yes,
Yes,
yes.
that's what I'm saying.
Yeah, so if this is a minus -1, if I were to simplify it, it would simply be X plus 1. But be really careful, because take a look at the way that the test wants you to fill it in. Does the test simplify it?
No.
No. So they actually want you to fill in -1 for that. So just be really careful with that. I just don't want you guys to
Freak out.
I don't want that to be the reason that you get this wrong. If you get this wrong, it better be because you have no idea what you're doing. But if you know what you're doing, make sure you pay attention to this very
I
specific.
don't know what I'm doing.
How is that helpful? It's not. Okay. Bo? You got your giggle. Is that good? Is that satisfying? Okay, good. All right, do you have a question, please?
yeah, so if it's X minus -1, but it's already in parentheses,
What?
because it's X minus -1.
Yeah.
But it's already in parentheses, it would be filled in when it says again. Oh, wait, never mind.
Yeah, there's no parentheses, it's just an empty box. The empty box in the answer key will protect your sign for you. Because you're not actually gonna simplify this. This is how you're gonna type in your answer. Okay.
Why is the vertex -170 instead of -0?
Because that's where the symmetry
Yeah, were you,
is. He wasn't here.
oh, you were in the bathroom?
Yeah.
Okay, maybe next time, can you make your bathroom trips like when I'm not in the middle of something? I will gladly explain it again, but we did just. Okay, so what we said was, we located that this is the vertex because if you look at your outputs, we see symmetry. If there's symmetry, that means the axis of symmetry is in between them. And the vertex is always on the axis of symmetry. It actually, the x value is the axis of symmetry because it falls on the axis of symmetry. So our vertex is -1, 7. And so I've got my -1 filled in, I have to fill in my 7. And then I still have something to figure out. What variable is this empty box actually representing? A, very good. So if I need to find A, let me rewrite that. I've got f of x equals A times x minus a -1 squared plus 7. Do you agree that it would just be easier if I just go ahead and simplify that?
I
if I wanna solve for A. I'll just go ahead and simplify it right here. Instead of dealing with all those parentheses. That makes it a little bit easier, right? Now, here's the problem. I want to solve for this value, but you can really only solve for a variable if it's the only variable there, if it's the only missing number. You can't solve an equation with two missing numbers most of the time. So, is there any information that we could use to fill in those missing numbers to make our variable A the only missing number in this equation? Yes.
Maybe.
Say it, you got it. You can do it.
You got this.
If it's wrong, I promise, we won't make fun of you too
I'm gonna say
much.
-1.
-1, fill that in for what?
X.
Yeah, but then we still have this as a missing number.
I put -1 in the X. So.
Yeah, but then I still don't have a value here. Okay, what is this? What is this?
That's why.
I forgot.
Yes! That's my output.
7.
So 7, yeah, we could do that. We could just put in the vertex there. Could I use, yeah?
0, right?
Yeah, now we can go back to 0, because 0 is such an easy number. So Jacob, you could totally use this. I would prefer to use this because it's super easy numbers. I don't have to deal with any negatives. You can use any point you want. Lily, I can tell you're zoning. Get your pen in your hand, okay? You can use any of these pairs because this x and this output function of x, that's supposed to be any point on the graph. So grab any point on the graph and plug it in.
Anything?
So I'm gonna use this pair just because I like that there are no negatives. So my output, my f of x is 4. My a is the one we're solving for. My x is 0 plus 1 squared plus 7. Notice how we now have a variable that is the only variable there. We can simplify and solve for a. Right, Bo? Can you put your hands on your desk, please?
Yeah.
No, I don't need any details. I would like you to put your hands on your desk so I can continue with the review. Sound good?
Yeah.
Okay. 0 plus 1 is 1. See how much we like zeros around here? 1 squared is 1. 1 times a is
1.
no. Tricked ya.
1A.
1a and
Just A.
1a is
A.
just a. We don't need that 1 anymore. So I have 4 equals a, and then don't forget about this guy,
Plus 7.
plus 7. Now it's going to be so easy to solve for a. What do we do?
Minus 7. So 4 and 7.
So we get -3 equals a. So that's what goes in my last box, or I should say my first box. -3 is our leading coefficient. Is it a happy parabola or a sad parabola?
Sad.
It's a very sad parabola. I'm so sorry. All right, we've got 2 more. You guys ready?
No.
All right. 2 more. The rate of change in the number of students at a high school, who cares where it is? I said, who cares where it is? That didn't say, hey, does anybody want to suggest a different school in place of that? Okay? The rate of change in the number of students at a high school was the same from 2011 to 2015 as it was from 2015 to 2019. The rate of change. Which type of function best models the data? I know you guys probably all have some guesses, and some of you are probably correct. Keep in mind that the way we do this class isn't just getting the right answer and then moving on, because then only maybe one person learned something, or didn't even learn it, they just already knew it. Let's look at each of these words and see how they relate to the information. First, let's define what a rate of change is. It's kind of self-explanatory, a rate of change. What does it mean? Or what do you think of when you think of rate of change?
Like it changes over a period of time. Like how
Yeah.
much changes over a period.
Yeah, something changes in relationship to a period of time or something else. It doesn't have to be time, but in this case, it definitely is. But sure. So what's changing in relationship to the period of time? Yes.
Number of students.
Yeah, the number of students. So if they say that the rate of change or the number of students per year or per month or whatever it is, it says that the rate of change is the same from 2011 to 2015 as it was from 2015 to 2019. What does that say about what this function might look like on a graph? Yes.
One straight continuous line.
What? Yes, it's a straight and continuous line. If it's a straight line, what, Uriah, you can say the answer now. If it's a straight line, what type of function best models the data? Linear, very good.
Why is it a straight line?
I'll show you in a second. Uriah, could you please not play with the calculators? What? Is it yours? Oh, then what were you saying? Uriah, when your teacher's speaking to you, you do have to respond, okay? You responded to me and I didn't hear you. I said, please don't play with the calculators, and you said something, I didn't hear you.
I was just rolling that with it.
Oh, okay. And I said, can you please not play with it? And then you don't have to explain the manner in which you were playing with it. You could just say, yes, ma'am. So simple, right? Nobody's in trouble. Just the teacher talking to you, and you can just respond. Okay, so what question did you just ask?
I said, why is it a straight line?
Oh, why is it a straight line? Okay, because I'm going to show you. I'm actually going to. I'll show you on my. I actually drew a picture of what it would look like in the notes here. Now, I didn't actually draw anything according to the information here because I honestly don't know if they're gaining students or losing students. I don't know if it's going up or down. I don't know how many students are getting here. They really don't tell us. But I did want to show that, let's say that this is, or I guess I shouldn't do it on the negative side and the positive side, but let's say the change in time goes from here to here, right? So the years are continuing. If the students are either growing or declining at the same rate, then I just gave this as an example. If let's say you get one student for every 2 years, okay? I know that sounds really weird, but that means that's the first time period. And if it's the same in the next time period, it would be one student for 2 years. And if it's the same, it would be one student for 2 years, and that would cause a straight line. Yeah? Yeah. Yeah.
So what's the difference between linear and constant?
Oh, good question. Because it's very confusing, because when we see the word same, it makes us think of the word constant. And that's because another way to say the same rate of change is a constant rate of change. So it's like, well, is that answer constant, like, part of the answer? It's actually not. And somebody got this in the last class, and I was very impressed. I want you to try to think of the answer to this question. If a linear function forms a line because there's a change and a continuous change, a continuous and constant change, what might the function of a constant look like on a coordinate plane? Yes?
you want me to answer the question or? can I-
Do you have to go to the bathroom?
No, I just want to be.
Go fill up your water then. Would it be easy if you guys just went to the bathroom and filled up your water as you please? This class is constantly leaving. Sorry, I don't mean to like single you out because it's not just you. But like, guys, it's ridiculous. We're in the middle of a review. You're supposed to stay and actually get some knowledge for your test. Do you want to answer the question?
Yeah,
Okay, go ahead.
like a linear change would be like it's changing the same amount over a year while a constant change is adding on to each other.
Nope. Yeah?
Can I hear like the question again?
Sure. So if a linear function
I
would,
don't want these Einstein.
that's weird. Thank you. If a linear function forms a line because there's a constant rate of change, that it's always changing, I'm sorry, it's always changing at the same rate. So it's like you have to go to the next point, the line continues. What would a constant look like on a coordinate plane? A constant, yeah.
Constant is always changing by that amount.
Think of what the word constant
Would
means.
it be good?
Constant is like, it has like 0.5 to 10 and like.
Let me ask you a question before you finish that. What is a variable? Yeah,
Any number,
it's a letter that represents a missing number. So that variable, whatever it is going to change when it becomes filled in, right? What's a constant?
A number.
A number. Does that number ever change?
So it's
No. What?
just like one big change instead of like the same thing.
Why do you guys keep saying the word change?
Cause you said it like 4 times.
Constant
It doesn't change.
is something that doesn't change.
It's the same.
So it's the same what?
I get
Same
constant.
rate
Same
of
rate.
change.
There's no rate
It's the
with a
same.
constant because a rate is moving.
It's just the same
What
change.
does a constant look like on a coordinate plane?
What did you think he like? I don't know if it would go like diagonal like this.
That would be a line.
Oh.
Angelina,
Would it just be like a coordinate? Just one?
it would be a point. Like a constant would be this point and nothing else. It would just be a point. Kind of like if this coordinate plane were, I don't know, like a map of the world. And this would be, I don't know, Bo's house right here. And unless there's some sort of crazy like Wizard of Oz tornado coming, it's not gonna move, right? It's a constant. That's what a constant is. A constant function. It's just like something that stays there and doesn't continue in any direction. Do you have a comment? Would you like to continue the shenanigans or can I move on? Okay. So that kind of explains why this is probably really never going to be the answer, unless they're talking about a house that never moves. If they're like, hey, there's a house on a map.
So not Dorothy.
There's a house on a map, and the house is built,
But
and it's
all-
not a mobile home.
But all houses move eventually.
Yep, okay, we're catching ourselves now, so, okay. So, constant, that's why, even though constant makes you think of, oh, well, constant means the same, so is a constant, yeah, that's what Savas wants you to do also, they're trying to mess with your heads. Binksy, wake up! Okay, so, constant's not it, linear is it. Let's talk about quadratic and exponential. Why can't this information refer to quadratic or exponential? Why can't it?
Kind of have a guess.
Okay, yeah.
Like if it's a name, like they are like quadratic can be like shape, like I don't know how to explain it.
Does a quadratic change from point to point?
No. Isn't this a square?
A quadratic function is a parabola.
Yeah.
Does it change from point to point?
They could.
Yeah.
What?
Can somebody show me a picture of a parabola with their arms, please?
I thought
let's say your elbow is a point.
Goal.
This.
Does that point change?
No.
Or the location change from that point to the next point, like my shoulder? Okay, and my neck, my vertex? Okay, so it does change. What is the rate of change next time into your elbow, okay? Is the rate of change the same from point to point? No, especially when you go past the vertex, it changes direction. That can't be the same. That can't be, so if this is saying the rate of change is the same, then that can't be quadratic. Tell me why it can't be exponential. Yes.
Because exponential, like whenever it keeps on increasing, it multiplies by itself.
Yes, very good. Exponential grows faster and faster and faster. So it's a little slow in the beginning, the changes are slow, and then it goes faster and faster and faster. And if it's decay, it's declining faster and faster and faster, yeah.
And
So-
also exponential, I like to think of it as like if you have something squared and like that square just keeps on squaring.
Yep, yep, so it's changing in a more drastic way the more you move
Like a-
on to the next point, yes. Okay, so we see how everything is kind of defined here. One more. This is also a little bit tricky, so pay attention, and I have 2 pages of notes for this one. You're welcome.
Thank you.
Okay. This table of values is poopy. First of all, they're giving me decimal numbers. I don't like that. And then all these y values are weird. They're just like all over the place, and they're big, and they're stupid, and I don't like them.
That's a no-no word.
No, it's not.
That's a what?
No word, we don't say
A
that.
no-no word?
Yeah, we don't say that here at Dixon.
I'm allowed to say it if I'm just being silly, but unfortunately, me being silly spurs on a bunch of shenanigans. So I won't. I'll just say, let's do number 10. This is how you do it. Complete the sentence to describe the model that best fits the data in the table. What do they mean by the model?
The model.
Yes, exactly. Yeah?
X and Y table.
No, they're not talking about the table because it says the model that best fits the data in the table.
So you gotta make one.
What do they mean by model?
Which form?
Complete the sentence to describe the model that best fits the data in the table. Yes.
What type of like function?
Yes, that's exactly it. Here's the sentence. A linear function, a quadratic function, an exponential function. One of these is the model or the graph. It's just a fancy word that means the graph or the picture of the function that best fits the data in the table. So we could take a look at this data and try to analyze it. It is just kind of all over the place and it's weird.
So it's not linear.
We
Sorry.
are going to take a look at 3 different types of, what?
No, wait, no, can you? Never mind.
Okay, so we're gonna take a look at these 3 different types of functions and what they look like in a table of values, but I'm not gonna use this very smart table here because it's very complicated, okay? I'm gonna show you guys what these look like with super easy function tables, and we're gonna notice the subtle differences between each table. Then we'll use what we learned from those tables and apply it to this question. First, let's talk about linear, our good old friend, the linear function. I made a linear function table. I simply did our usual x values, 0, 1, -3, -2, -1, 0, 1, 2, 3. I did it horizontally, just like the question, just to keep things consistent. And then we have an output here. The thing that I want you to notice about these values is that the difference between each output value is 2. We call that a constant difference or a common difference. Constant and common meaning the same thing here. And we call this a first difference. Why What do you think calling it a first difference implies about what I'm gonna say next?
It's a difference you do first.
And if it's a difference you do first, then there's gonna be a second difference, right? Now, I will talk about what a second difference is in the next table. But here, we can define or identify this table as a linear function table because we have proven that there is a first difference, and that simply means it's a constant or common difference, which is a slope, right? So we're adding 1 to each input and adding 2 to each output. So up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, that's a slope. So a common difference or a common first difference makes a slope, and that's why we would call this linear, because a slope makes a line. Are we good? Let's take a look at our good old friend, the quadratic table. Same inputs, let's look at these outputs. We do see the symmetry here. So it's very easy to identify this as quadratic when it shows you the portion of the table that actually contains the vertex. But what if, spoiler alert, it shows you a portion of the table that doesn't contain the vertex? It's very hard to identify it as a quadratic function, although we still will. The way we're going to identify the quadratic function isn't by its vertex and symmetry. We're going to identify it by its second difference. That means we find the difference of your y values. You always do the second y minus the first. 4 minus 9 is -5. 1 minus 4 is -3. 0 minus 1 is -1. So on and so forth. This first difference means nothing to me. There's nothing the same about it. But if I take that first difference and I do the same thing, and I start subtracting the second one minus the first one, and the third one minus the second one, and the fourth one minus the third one, and I keep going, the difference of each of these is going to be the same. A quadratic function always has a common or constant, those words are interchangeable, they always have a common second difference. Now, here, I wrote this because I just want to show you that in this example, if you get out your calculator and you do 35 minus 8, 54 minus 35, 65 minus 54, you're going to get all these wacky numbers. You're going to be like, I don't get it. I don't know what it is. Well, take that first difference and see what the second difference is. 19 minus 27, -8. 11 minus 19, -8. And I know I'm going fast, but when you do this with the calculator, it goes nice and fast. You're going to see that there's a common second difference in this table from question 10. What's with the surprise faces?
You're like an acapella in the bathroom.
Oh, I can't even hear it because I'm so focused on the review. Okay. So, do you guys see that this is quadratic because it has a second difference? You're going to want to take notes on this when you get home. But you're going to definitely want to pay attention to the third one, because what if that shows up? The third one is exponential. We've studied exponential tables before. No packing up. We've studied exponential tables before, and we have seen that there's no difference between no stacking of papers. There's no difference between these. I mean, the numbers are different, but there's no common difference. But there is a common ratio. What do I mean by common ratio? Same what?
Same thing.
But what's a ratio?
A fraction.
Yes.
Fraction.
Yep. So what it means is that each You guys think that I don't know that the period's over? I know the period's over. You guys want to go? This might be on your test. Anybody who wants to pack up and go, just go. Anybody who wants to stay and let me finish my sentence can stay. What you'll notice about exponential tables is that from one y value to the next, you're multiplying by the exact same number. It's called a constant ratio. It's as simple as that, but you actually have to pay attention and stay the extra 30 seconds of class to get the information. I hope you guys have a wonderful day, and I hope you take really good notes tonight.
You